Hello student, welcome to my YouTube channel IIT Jam in Organic Chemistry. Those who are new to my channel, subscribe to my channel to get updated, to get new videos. In my first lecture, I discussed about the last 5-6 years question paper analysis, where I also discussed the last 5 years cutoff and the expected cutoff for IIT Jam in chemistry, and also I discussed that how many marks you can expect from inorganic chemistry so that you can prepare accordingly. I also told that I will discuss the whole syllabus topic wise. So today I am going to discuss about one of the first topic that is there in your syllabus at IIT Jam, that is periodic properties of elements. Now you can expect directly 2 marks from periodic properties, but it is very important to understand, to clear many concepts in inorganic chemistry. It will help you to understand chemical bonding, it will help you to understand many reactions in main group elements, D block elements, coordination chemistry, as well as organometallics, and also to understand reaction mechanisms. So it is one of the fundamental chapters that every student of chemistry must know about it. So what are there in the syllabus in your IIT Jam, or even the same syllabus is there at CSIR NET also. So in periodic properties, the most important part that you need to study, effective nuclear charge, or sometimes it is known as Slater's rules or shielding effect. Then you need to understand atomic and ionic radii, which is again very important. Then ionization energy, electron affinity, proton affinity, and electronegativity. So if you read these few topics, it's more than enough for your IIT Jam and also for CSIR NET. So now I am going to start with effective nuclear charge. Now this is very important, and you can expect at least one questions in CSIR NET as well as Jam. And if you analyze last 5 years, there are more than 2-3 questions have been came from effective nuclear charge, directly or indirectly. So what is effective nuclear charge? It is nothing but the actual nuclear charge experienced by electron in a polyelectronic atom. So let us consider a polyelectronic atom. Polyelectronic atom means where the number of electrons is more than 1. So let us consider an atom where we have many electrons in different shells. Let's say for example, this is where we have 2 electrons in 1s, then 8 electrons in 2s and 2p, where n equals to 2. Then we have 18 electrons where n equals to 3, and we have few electrons in n equals to 4. So now let's say I wanted to know that how many nuclear charge an electron in 3D cells actually experience. So all the electrons which is lower than 3D, they will try to reduce some nuclear charge, and thus the actual nuclear charge that will be experienced by an electron will always less than the actual nuclear charge. That means the electrons in a polyelectronic atom, they are shielding some of the charge. That's why it is known as shielding effect. And the electrons which are above that target electron, let's say our target electron is this. This is the target electron for which we wanted to calculate that how many positive charge this electron actually experiences. Now I have to only consider the electron present in this cell as well as the electron present below these cells. The electron which are present above these cells or which are in outer cell, they will not shield anything, because anyhow this electron will be affected only by the electron which are in the same cell or the lower cells. So now how to calculate this effective nuclear charge? So effective nuclear charge is nothing but the actual nuclear charge and if we subtract this by the shielding constant, then we will get the effective nuclear charge. So sigma is nothing but the shielding constant, which will tell you in numerical form that how much charge has been reduced from the actual nuclear charge. So now I am going to explain how to calculate this shielding constant or sigma. If you can calculate sigma, you already know the actual charge from the atomic number, so you can easily calculate the Z effective. Now in your exam, mostly they either wanted to know the effective nuclear charge, or sometimes they ask that what is the shielding constant or what is the value of sigma. Now in general there are two cases that you may encounter in your exam. You may be asked to calculate the effective nuclear charge for either sp electrons, that means electrons can be in s orbital or in p orbital, or in another case you can be asked to calculate effective nuclear charge for b and f electrons. So there are two different set of rules which are there to calculate shielding constant. These rules are given by Slater and sometimes known as Slater's rule. So to apply Slater rules, or what is the Slater rules, you must first write electronic configuration in this way. You need to forget the above principle. We need to write the electronic configuration in this way. That means 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4a, 5s, 5b, 5d, 5f, and so on. That means you have to write in the increasing order of n. Please remember, because sometimes you may get confused that you may need to write according to above principle, but to apply the Slater rules, you have to write the electronic configuration in this way. Then only you will be able to apply Slater rules, and you can get this effective nuclear charge by applying this equation. So now what are the rules? For ns and np electrons, first I will consider. Let's say we have chlorine atom where the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. This was a mistake. So I will apply the Slater rules. What Slater rule says that for all other ns np electron, that means let's say we are wanted to calculate the effective nuclear charge for the last electron in p orbital. So in n equals to 3, 3s to 3p5, so there are total 7 electrons. We wanted to calculate the effective nuclear charge for 1 electron. So that means we are left with 6 electrons in n equals to 3. So that means for all other ns np electrons, that means all electrons which are left there, they will contribute 0.35. For all electrons of n minus 1 cell, that means if n equals to 3 here, so n minus 1 will be 2, that means 2s and 2p electrons in this case will contribute 0.85. So you need to remember that all ns np electrons will contribute 0.35, all n minus 1 electrons will contribute 0.85, and all n minus 2 and lower cells, they will contribute 1, that means they shield completely. So now let us calculate the shielding constant and effective nuclear charge for this polyelectronic atom. So we have 7 electrons in NSNP, but we wanted to calculate for the last electron, that means there are 6 electrons left. So as per the rule, 6 into 0.35. Then in n minus 1 cells we have 8 electrons. So 8 into 0.85, and n minus 2 cells we have only 2 electrons. So 2 into 1. Altogether you have 10.90. That is the value of sigma or shielding constant. In many exams they ask what is the value of shielding constant. So this is the way to calculate shielding constant. You can apply to any system if you need to calculate S and P electrons. You can apply this rule. Now, what is the Z effective? The actual Z or the value of Z is 17 here, and we have to deduct sigma, that is shielding constant, and we can get 6.10. 17 minus 10.9 plus 6.10. So that means your Z effective is 6.10. What is the significance? That means an electron in pure metal we only see the nuclear charge of 6.10. It will not see the total 17 nuclear charge. So that's how the Z effective helps to calculate many properties. It helps to understand ionization energy. It helps to understand atomic and ionic radii. Z effective also very important to understand electronegativity. That's why it has lots of applications, and in the upcoming lectures I will probably discuss many applications of Z effective when I will discuss ionization energy, electron affinity and electronegativity. So now this is the case for NS and NP electrons. Now let us have this kind of situation that we need to calculate the effective nuclear charge for a d electrons. Then what are the rules? For d and n electron, Slater has suggested that all ND NF electrons other than the electron we are trying to calculate. Let's say we are trying to calculate the Z effective for a 3D electron in chromium. So now what are the rules? For all other D and F electrons they will contribute 0.35. All other electrons except ND and F, whether it is n-1 or whether it is n-2, you need not worry about it. Except D and F electrons, all other electrons will be contributing 1. And then you need to apply this formula, Z effective equals to Z minus sigma, and you will get the Z effective value. Now let us take an example of chromium. Now the electronic configuration of chromium is, you know that 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1, 3d5. Now if you want to apply Slater rules, we have to write the electronic configuration not by above principle but by this way. That means 1s, 2s, 2p, 3s, 2p, 3d will come first and 4s will come later. Now we wanted to calculate the effective nuclear charge for d electron where it is 3d electron n equals to 3. So n equals to 4, this electron is above than this n equals to 3, that is 3d. So this 4s electron will not contribute anything to the Z effective, or it will not contribute to the shielding. That means we need to only consider the electrons which are present in 3D and which are present in lower than 3D electrons. Because these electrons are in outer shell, it will not contribute to the shielding. So what are the rules? Already explained that 0.35 will be contributed by all other ND-NF electrons and all other electrons other than ND-NF will contribute 1. Now let's apply this rule. Now we have 5 electrons in d orbitals, so we are wanting to calculate for 1 d electrons. So there are 4 electrons left. So 4 into 0.35 plus there are total 8 electrons in outer, in lower than 3d cells. So that means they will all contribute 1. So 18 into 1, altogether sigma or shielding constant is 19.40. So the Z effective will be 24 minus 19.40, which is equals to 4.60. So now I think it is clear to you that how you should apply Slater rules for NS and NP electrons, ND and NF electrons. With this formula you can apply to any elements present in the periodic table and you can calculate sigma as well as Z effective. For your IIT JAM or CSIR net, sometimes the atomic number is given, or else you can easily remember the atomic numbers and you can calculate Z effective, sigma, and accordingly you can predict many properties. So your life become easier if you understand the effective nuclear charge. So this is the first topic that you need to study. So now you can take the screenshot or you can take screenshot for the later view. So another important property that I am going to discuss in this lecture is atomic and ionic radii, because most of the properties of elements depends on atomic and ionic radii. Their reactions, their many products, their coordination number, they depend on ionic radii. Their solid state structures depend on ionic and atomic radii. So now what is the basic trend in atomic and ionic radii? The basic trend is in a period from left to right side, the atomic and ionic radii decreases, and in a group from top to bottom, the atomic and ionic radii increases. If we apply the same rule, you will find that lithium greater than barium greater than boron greater than carbon, nitrogen greater than oxygen greater than helium. Now why I took neon as the first? Because of the van der Waals radii. This is not the atomic radii, this is the van der Waals radii, and neon has the, that's why it is the highest van der Waals radii, and we have brought it at the beginning. Now it will follow the same way, where it will decrease from top to left to right. So this is very easy to understand. Now in case of, in a group, again they start increase. That means cesium has the highest atomic radii as well as ionic radii, lithium has the lowest. Same as the case for all the other groups. So there are no such kind of discrepancy, or there is no exception. Only thing is that when you encounter d elements and the elements which are just after the d elements, because of the d contraction, sometimes you may encounter that two elements having similar size. For example, silicon and germanium, although silicon size, germanium size is little higher than cesium, but not very larger than silicon. Silicon has I think 117 ppm, that is picometer radius, and germanium is only 122 picometer. That is they are very very close because of the intervention of d contraction or d electrons, which we will discuss when I will discuss about the d block elements. Now for time being, you must remember that in d block elements they do not follow any kind of rule in terms of atomic radii or ionic radii, and because of the lanthanide contraction, some d block elements in 4d and 5d series, they have almost similar kind of atomic radii. That's why sometimes you may encounter this kind of questions, that which of the following pair of elements having the similar sign. That's why I wanted to explain here that there are 4d and 5d elements which have similar signs because of the lanthanide contraction. Now why lanthanide contraction happens, that I will discuss during the F block elements discussion, where I need to tell that why F block elements, why F electrons are poorly shielding and they are highly shielded, and that's why because of their less shielding effect, sometimes this atomic radii contracts because of the effective nuclear charge. There are more attraction between the nucleus and the F electrons. That I will discuss during the F block elements discussion. So now zirconium and hafnium, niobium, tantalum, molybdenum, tungsten, silver, gold, cadmium, mercury, rhodium, iridium, palladium, platinum, ruthenium, osmium. These are the pairs where the two elements having the similar size. For example, if I talk about niobium and tantalum, they have exactly similar atomic radii. If we talk about silver, gold, they have exactly similar atomic radii because of the lanthanide contraction or F contraction. Now, this kind of questions also you may encounter that. So, the first one, that is 3D series elements, they are quite follow this kind of trend. That means titanium greater than zirconium, which is almost equal to aluminium. So, this kind of trend generally followed. So, now if you analyze the question paper, you will encounter this kind of problems, right? But I will again discuss in more detail during B block elements. Now come to the A block elements. What are the trends in atomic and ionic radii? Here we will say it's metallic radii. Now metallic radii decreases from lanthanum to lutetium, but there are two exceptions. Europium and ytterbium, they have the largest metallic radii. Please remember, this concept came multiple times in CSI net as well as in GM also. There is a probability that this type of question may come. And this is the reason. What is the reason? Reason is in europium 4f7 and ytterbium 4f14 electronic configuration appears. Now why this happens? Again I will discuss in detail during A block elements, because there you need to understand the radial probability functions of S, P, D and F orbitals. That is beyond the scope of today's discussion. Now in case of ionic radii, there is no discrepancy. The radii decreases from left to right, that means starting from lanthanum to lutetium. Radii, ionic radii, that is lanthanide 3 plus, because lanthanide show plus 3 oxidation state. So lanthanum 3 plus to lutetium 3 plus, ionic radii decreases steadily, and this decrease is so steady and smooth that is not found in any groups or any periods in the periodic table. Why this happens? Because Z effective increases smoothly from lanthanum to potassium. Now we need to understand why Z effective or effective nuclear charge is so important. So because the effective nuclear charge increases, the attraction between the outermost electron and the nucleus increases and the size decreases. So that's why lanthanum 3 plus plutonium 3 plus size decreases steadily. So this is about your atomic and ionic radii, where you need to only remember few things about d block elements, few things about the a block elements, other all followed normally general trend. So that means today I discussed effective nuclear charge, where you can calculate the effective nuclear charge and Schelling constant for S and P electron as well as D and F electrons by applying Slater rules. I also explained atomic and ionic radii. So sometimes the trend in period and groups comes in the exam, where I also explained few exceptions in D block and A block elements. So now in the next lecture I am going to explain about ionization energy, electron affinity, proton affinity and electronegativity. So once again I welcome you all. Those who are new to my channel, subscribe it to get updated videos, and if you have any doubts you can write in the comment section. If you need any topic need to be discussed, or if you have any kind of questions, you can type in the comment section and I will come and I will try to discuss. If you need any live class, you can also give in the comment section. I will plan the live class where you can interact with me directly. Thank you once again. All the best for your IIT channel.